In this video, we will introduce our work sign language translation with Iterative Prototype, a simple yet effective framework for sign language translation. The goal of sign language translation is to automatically convert a sign language video to its corresponding spoken language translation. Sign language translation is a challenging task, which faces a tough domain gap between the input video and output text, as well as a limited dataset scale due to costly data collection and annotation. Since sign language translation is typically viewed as a sequence-to-sequence mapping problem, the existing sign language translation systems commonly adopt the one-pass forward process based on encoder-decoder architecture. In such a framework, the encoder transforms the sign language video into its semantic representation, that is, a prototype, which is then fed into the decoder to generate the translation. However, due to the inherent gap between vision and text, it may be hard to conduct such mapping within the vanilla one-pass architecture. We note that during reading, repeatedly digging into the source materials is necessary for accurate understanding. Similarly, when we are trying to translate a sign language video into a sentence, we commonly do not directly write it down. Instead, we would go back to the original video to check our answers. To implement this idea, our approach adopts a recurrent structure that enhances the semantic representation of the input sign language video via an iterative refinement process. To leverage the sequential dependence between different iterations, we further propose the iterative distillation loss, which allows the previous prototypes to obtain supervision from the final one. Here we present a quick overview of sign language translation with Iterative Prototype. Given a sign language video to be translated, the feature extraction module embeds it into a visual representation. Then, the initialization module generates the initial prototype and the raw translation based on the visual representation. Subsequently, the refinement module iteratively updates the prototype toward the semantic meaning of the sign language video. At each iteration, the module refines the previous prototype by aggregating it with the original visual representation. Through iterative refinement process, the prototype finally converges to a stable and accurate state, producing a better translation. Since only the final prototype is used for the autoregressive decoding process, the parts enclosed in dashed boxes can be removed in inference. To utilize the prototype as a reference, each layer of the encoder attends over the maintained semantic features through the attention mechanism. In this way, we inject the rich semantic information into the new prototype. As for the training objective, we introduce two kinds of losses. Firstly, the cross-entropy loss is commonly used for sign language translation, which is computed with the ground truth and the output of the system. We apply this supervision at the output of the initialization module and the final output of the refinement module. Secondly, we propose the iterative distillation loss to encourage the model to approximate the performance of the final iteration. It is computed between the intermediate predictions and the final prediction. We evaluate our approach on two public sign language translation datasets. Both datasets provide gloss-level and spoken sentence-level annotations. On both datasets, we compare the proposed method with the previous sign language translation systems. We adopt the STMC and BNTIN transformer as the baseline, respectively. Note the last two methods adopt pre-trained large-scale language models that leverage more model parameters and extra resources than our approach. By combining all proposed components together, our approach achieves promising performance improvements against the baseline. The results prove the advantage of leveraging the iterative refinement process, which distinguishes our approach from previous methods. Moreover, we conduct several experiments to validate the proposed method. The results suggest that gradually applying the proposed process to the baseline delivers continuous performance improvement. Besides, we compare our approach with the non-sharing weights method between different iterations and conduct 3 sets of experiments by changing the visual backbone. As we can see, the proposed parameter shared method achieves near performance gain with non-shared one but leveraging much less parameter number. Comparing with the baseline, leveraging the iterative refinement process causes acceptable overhead while achieving promising performance improvements. Thanks for your listening.